Okay, so today we're going to start looking at, sorry about that, we're going to start looking at the neural nets. Just before we start, here's a little bit of logistics for the course. Assignment 1 is going to be out today. It's going to be due in 2 weeks. Everybody should be registered here on Gradescope. That's the software we're going to be using, where you will be able to upload your homework, your code, and everything. So I'm also going to put the assignment later today on the website. But again, you should all look at Piazza. I think one of the TAs announced that you're going to be added on Gradescope. If you haven't been added to Gradescope, make sure that you are. Ping TAs, make sure that you are in the system. Because what happened last year is that, 2 hours before the deadline, students are saying, where am I supposed to be submitting it? And what is this thing called Gradescope? And I'm out. And so now there's been a bunch of delays, and you don't want that, okay? So make sure that you are in the system. We're going to be using it through all the assignments and projects and such. You have 2 TAs specifically dedicated for this assignment, Dirash and Hubert. These are the office hours about the homework. So these are Thursdays, Mondays, and Fridays, okay? So you're more than welcome to talk to TAs about, during the office hours, about the assignment. The assignment is going to be due on Monday, right? So, and based on previous experience, most of you will start working on the assignment on Sunday before it's due. So there aren't going to be office hours, on Sunday, right? So be careful not to do that. The assignment itself is, I think that the first part of it is not very difficult. The second part, you're going to be training a neural net and using backprop and so forth. So it is something that you have to start pretty early. So don't delay. If you start working on this assignment 2 days before the deadline, depending on how confident you are, you can do it. But I doubt it, right? So don't delay up until the end. And again, you're going to be training a whole bunch of models. You're not required to use GPUs. If you have a GPU, that's great, but the assignment is designed to run on your laptop, on your desktop, provided that you give it enough time to run these models, right? Don't expect that you're going to be running these models, in like 5 minutes, 10 minutes, and you get the results, right? So look at the assignment today, look at the material, make sure you have everything, you have Gradescope, you understand the assignment, you have TAs this week, next week, make sure you use the resources, okay? Now, we're going to have a midterm on October 9th, which is Monday, October 9th. We're still trying to figure out the logistics. Maybe we're going to get a separate room. It's going to be in-class midterm for 1 hour and 10 minutes. And you will have, after the after the first assignment is out, September 25th, when it's due, you're going to have basically 2 weeks to study for your midterm. So please take that time and study for the midterm. The second assignment will be out on October 9th. Once you're done with your midterm, you'll be delighted to study for work on your next assignment, right? And we're going to keep up with the pace. You're going to be pretty busy in this course. One thing to point out is that we're not going to have class on Wednesday. So this Wednesday, we will not have a class. So tell your friends or whoever is taking the class, and we'll announce it on Piazza. We will not have a class on Wednesday, okay? So take that time and do the homework. Or at least read through the homework, right? That's very important. Just read through it today, tomorrow, so that you have some idea of what is it difficult, is it not difficult, and so forth, right? So focus on your homework. It's your first homework. I don't think it's very difficult for this level course, but it will require you to actually do some work, right? You will have to spend some time on it, particularly if you haven't had experience training these models. One point about the homework, you can use Python, you can use C++, you can use whatever language you want to use. but you're not allowed to use backpropagation algorithm implemented in TensorFlow or PyTorch. You're going to be running your own algorithm, okay? Because if you could use it, the whole assignment would be very easy. You just modify a few settings, look at the results, modify a few other settings, look at the results. The point is that you're going to be writing your own backpropagation algorithm. You're going to be writing your own dropout, your own batch normalization, your own 10H, ReLU activations, all that stuff. And you're going to be hitting lots of underflow, overflow. You're going to be hitting a lot of things, right? Especially when you start doing it from scratch on your own. So make sure that, again, that you start as soon as you can. Okay? Any questions? All right. So today we're going to start looking at neural nets, and we're going to go through it fairly quickly, because hopefully after today's lecture, you will be able to do most of the assignment, pretty much 80% of the assignment. And next Monday, we're going to cover more advanced techniques, something that, again, you'll need for your assignment. Okay, so you can, after today's course, you'll be able to do basically 80, 90% of the assignment. So that's good. I'm going to be using materials and slides coming from Hugo Larochelle's course. So that's, you're more than welcome to look at his material on his course as well, as actually he's put a lot of efforts in designing MOOC-like course. So for some of the materials in this class, that's an excellent resource. Okay? And here's the website and such. So you can go through multiple lectures as well. Okay, so what are we going to do today? So today, we're going to look at the neural nets, which is, you can think of them as predictors. We're going to look at forward propagation. We're going to look at types of nonlinearities, hidden units, capacity of neural nets. And we're also going to go through how do we train neural nets, the loss function, as well as backpropagation algorithm. Okay? And you will have on the web, you'll have these slides. You'll have reading material. And basically, I would encourage you to go through these slides, because they get fairly notational-wise and such a little bit complicated. So you kind of have to go through them carefully. On next Monday, we're going to cover more recent techniques like dropout, batch normalization, and supervised pre-training. And again, both of those things are going to be on the assignment, on your first assignment. OK, so let's look at the first thing. Let's start with basics. We're going to be denoting bineuron pre-activation or input activation as just a linear combination of the inputs, right? It's almost like a linear model. You have some input, x1 up to xd. You take a weighted average of those. You add a bias. And that's what we're going to be calling the pre-activation, a of x. Okay? The neuron output activation, we're going to be denoting it by function g. Okay? So g is going to be some kind of nonlinearity. Sometimes it's also called activation function. So we have pre-activation, which is just the linear combination of the input. And then we have output activation, right? So this linear combination will then go through some nonlinearity. Okay? Now, in many cases, when we look at this nonlinearity, and when we look at this particular nonlinearity, the range is going to be determined by g, right? What's the range of the output? And biases will only change the position of the rift, right? So the bias will basically scale things up and down, much like what you see in linear regression or logistic regression. In fact, when g is a logistic function, then this almost looks like a logistic regression, right? So some of the activation functions, sometimes people use linear activation function. There's no nonlinear transformation, no input squashing. Sigmoid activation function is probably the most used one. And it squashes the neuron's output between 0 and 1, right? It's always positive, it's bounded, and it's strictly increasing. Okay? So it's always bounded between 0 and 1. It's a sigmoid activation function. Okay?
When A is 0, then where do you start 1?
So when A is 0, it's going to be 0.5. So now hyperbolic tangent function, 10H function, that's also commonly used 10H function, particularly it squashes the neuron's activation between -1 and 1, right? So sometimes people prefer to have symmetric type of representation, 1 minus 1. Sometimes people prefer to use sigmoid function because it gives you, zeros. It can be negative or positive. It's bounded, it's quickly increasing. No, that's the right plot. I actually fixed it. That's the right plot. It used to be wrong plot. So this is the right plot. It goes from -1 to 1, right? 10H activation function. Sometimes you see people using it, but not as often as sigmoid nonlinearity. There is also a class of functions called rectified linear activation functions, ReLUs. Right? It's bounded below by 0, so it's always non-negative. But look at this activation function. It basically takes the neuron pre-activation. If it's positive, it's linear. If it's negative, it's just set to 0. It's not upper bounded, and it's strictly increasing. ReLUs activation functions are probably the most dominantly used ones in practice, particularly when we look at convolutional networks and so forth. This is the dominant function to use. Sometimes people bound it above by essentially saying, well, if the output is above 10, let's say, I'm going to clip it at 10, just to avoid instabilities in the model. But generally, that's the function people prefer to use. The nice property about this activation function is that when you compute the derivatives and you backpropagate through this max function, you can see that if it's positive, it's linear. So effectively, you don't really have to exponentiate anything. Every time you're using 10H or sigmoid, you have to use exp somewhere. And exp can be expensive operation. So these kind of nonlinearities are a little bit more efficient to train with. Okay? So people are commonly using them. Now, let's look at the decision boundary. If we're using sigmoid, you can interpret the neuron as estimating the probability of target being 1. So you can interpret it as a logistic classifier, right? For example, if you have x1, x2, with a sigmoid, you can have a decision boundary. This is 0, this is 1. So if activation is greater than 0.5, you predict 1. Otherwise, predict 0. Right? Think logistic regression. That's a single neuron. That's what single neuron is doing. And same idea can be applied to 10H activation functions. You can solve linearly separable problems using a single neuron. Right? So you can solve problems like or AND. But you cannot solve nonlinearly separable problems. Right? So for example, XOR. A single neuron cannot solve this problem, much like logistic regression cannot solve this problem. Right? Because there's no linear separator that separates the two classes. So you need to transform the input into better representation. And remember, I think during our first class, we looked at the radial basis functions. I'm looking at the input, trying to come up with some nonlinear transformation of the input and go to some feature space where the decision boundary becomes linear, right? So that's one approach. Now, if we start looking at the single hidden layer neural networks, let's look at what they look like. It's just the one layer. So we have pre-activation, right, which is the weighted average of the inputs. Then we have a hidden layer activation. So every single hidden layer, now is that you have pre-activation, you go through nonlinear function, right? So A of x, it goes through some G of x, and G of x is some nonlinearity like ReLU or sigmoid. And then we have an output layer activation. And the output activation could be some other output function, depending on what the task is, right? So for example, if we try to solve multi-way classification problem, then output would be softmax function. If we try to solve binary classification problem, the output would be a logistic function. If we try to solve some regression problem, maybe the output is just going to be the identity function because that's going to be the output of just the mean of the Gaussian, right? So depending what your target, what you're trying to solve, you can have different activation functions, which can be different from activation functions of hidden nodes. Okay? So if you think about it, it's almost like you're sticking together a whole bunch of logistic regressions, right? This is a logistic regression. This is a logistic regression. This is a logistic regression. But the nice thing about neural networks is we're not providing targets for each individual hidden units here, right? The target is only provided at the very top. So we'll see how we can use backpropagation algorithms to actually train this entire system jointly. So let's look at softmax activation function, okay? Which is what you're going to be doing on your homework. So for multi-way classification, we need multiple outputs, one output per class. Okay? In your homework, you're going to be working with MNIST dataset, trying to predict the class of the digit. And so you're going to have multiple outputs. You're going to predicting 10 classes, you're going to have 10 outputs. And we need to estimate the conditional probability. What's the probability that you see a particular class given the input? And this will belong to a class of so-called discriminative learning, because we're going to be trying to fit these probabilities. Given the input, try to predict the output. Or given the input, try to predict the class, the probability of a class. Okay? So the softmax activation function at the output has this form, right? Which is, this is pre-activation, which is the weighted average of the hidden units below your output layer. And then you exponentiate it. You exponentiate A1 if you have C classes, right? You have C outputs. In MNIST case, you're going to have 10 outputs. So you exponentiate, and then you renormalize. So this whole thing sums up to 1, right? That's the sum over here, okay? So that's going to be your output. You know, if you want to say, what's the probability that this digit is 1? Well, you take the weighted average coming to that particular node, you exponentiate it, and you normalize it, right, across all 10 different classes. And you're going to be predicting the class with the highest estimated class conditional probability. So you pick the one with the highest probability, right? Because these all will sum up to 1. Now, if we look at the multi-layer neural networks, what's the idea? The idea is actually very simple. We're going to have, instead of having one hidden layer, we're going to have L hidden layers, right? So we're just going to repeat the same operation L times. So for each particular layer K, this is the weighted average. HK minus 1, when K is 1, we just have the data, right? Take the weighted average, push it through nonlinearity, repeat, right? So he's take the weighted average, push to nonlinearity, take the weighted average, push nonlinearity, take the weighted average, push to nonlinearity, and then you get the output, right? So it's just a bunch of these modules basically stitched together. And then you have the output, which is your output of your neural network, f of x. Yes?
Is G the same in all the layers?
Yes, in this particular case, G is the same for all the layers. People have tried looking different Gs for different layers, but it's not clear why you'd want to have that, unless you have a particular reason to do that. Generally, for most of the models, G is the same for all the layers, like ReLUs everywhere, or sigmoids everywhere, or 10H everywhere, except for the output. The output could be softmax, could be just a logistic function, or sometimes people, you know, if you're predicting Poisson distribution, you know, try to model some spikes of, you know, neurons firing, the output is going to be a Poisson model, okay? Now, the capacity of neural nets, that's where the interesting part comes in. Let's look at the single layer neural network, right? Remember what each one of these hidden units is doing. Each one of these hidden units is basically doing linear separation, right? It's trying to separate, this is trying to separate, but when you combine, you can actually have fairly, you know, sophisticated decision boundaries, right? You can carve out a lot of things together. In particular, you know, this is an example where each neuron, you know, carves the space, but when you look at the overall output, it can actually be quite complex, right? It's like sometimes people think of this as wisdom of the crowd. You know, you ask each individual person, and even though each individual person might not be smart, like these hidden neurons here, like they're just doing linear separation. When you combine all of them together, you can actually have fairly sophisticated decision boundaries, right? So for example, here's an example that, in fact, with a single layer neural net, you can come up with decision boundaries that look like this, right? So this is class 2, and this is decision boundary for class 1. So you can kind of model this class and have these complicated decision boundaries, right? Yes?
Is this any better than using boosting?
In many cases, we'll see. Yeah, in many cases, it is better. Boosting, and we'll come back to that. But generally, the idea behind these models is that they're highly adaptive, and they can model fairly sophisticated decision boundaries. That's what makes these models pretty powerful. There is actually a theorem that was proved back in 91, which is essentially saying that a single hidden layer neural network with a linear output can approximate any continuous function arbitrarily well, given enough hidden units. Right? So it's a pretty powerful statement, even though it's sort of pretty easy to see, right? Because what I can do is, if I have some kind of function, nonlinear function, what I can do is that you can sort of do piecewise linear approximation to it, and each hidden unit can kind of look at a specific piecewise linear approximation. So it's not, it's not surprising, but it does tell you that these models can be quite powerful. But it doesn't mean that there exists a learning algorithm that can find the necessary parameter values of this neural network. It says that there exists one, but it doesn't tell you anything about how you can learn one, right? How many hidden units you need and so forth, right? Any questions here? So, yeah, go ahead.
Is there any increasing capacity that is given by adding multiple hidden layers?
Yeah, we'll come back to that. It's not clear. This is kind of like a debate. Do you get more capacity as you increase the number of hidden layers? This theorem is telling you that I can do everything I need to with just one hidden layer. So from theoretical perspective, all you need is just one hidden layer. It just doesn't tell you how to get there or what the learning algorithm should be. In practice, people do find that multiple layers generalize better, they perform better. And so, but I don't think there is a substantial theory saying that, one is better than the other. Okay, so let's look at the following. First, let's look at the loss function, and then let's look at the backpropagation algorithm, right? Something that you will need for your first homework. And based on previous experience that I had going through the backpropagation algorithm, a lot of you will come out and be very confused. So go through the math behind the algorithm once. It's kind of interesting. It took people about 30 years to figure that out. But once you figure that out, it's actually pretty easy. It's like simple calculus, right? Nonetheless, okay, let's look at the loss function. What is it that we're trying to optimize? We're going to be looking at empirical risk minimization, right? So let's look at what we have. We have T training examples, okay, number of examples. Let's say in your homework, you're going to be working with 300 or 800 examples. You have a loss function. Your loss function is, again, telling you this is your prediction, right? These are class conditional probabilities, for example, and this is your target. This is telling you which is the correct class, right? So generally, your loss function will look at the predictions, look at the correct output, and measure some fit. How good is this fit? How well is your model doing? And then you're going to have a regularizer. And the regularizer will come from, bias variance decomposition that we've looked at one of the previous classes. So learning can be cast as an optimization. So generally, this is an optimization problem, right? We're just trying to minimize with respect to the parameters of our neural network. So if we try to do classification, ideally, we'd like to minimize the classification error, right? So it seems like the right thing to do. I want to make as few misclassifications as possible. But it's often hard to optimize this objective function directly, right? Because it's non-smooth. So in many cases, loss functions can be viewed as a surrogate for what we want to optimize. For example, an upper bound. And we'll see that when we're doing classification, for example, so I'm trying to solve a classification problem, we're actually going to be optimizing a different function. We're going to be optimizing cross-entropy error or negative log likelihood, which is a proxy for what we want to optimize. Now, let's look at how you would implement stochastic gradient descent for a neural network. So we're going to be performing updates after seeing each example. On your homework, you can do stochastic gradient descent, or you can do just batch learning. You can compute the gradient for the whole thing. It's up to you. But typically, stochastic gradient SGD typically is faster. It's much faster to converge. So going to be initializing parameters of multiple layers of a neural network for iteration 1 to t, right? Typically, t is some hyperparameter that you have to set. For each training example, x and y, so here's your input, here's your target. In the case of MNIST classification, x is going to be your image, bunch of pixels. Y is going to be the class label. Is it 3, is it 5, is it 6? You're going to be computing the gradient of the loss function with respect to the parameters and the gradient of the regularizer with respect to the parameters. Okay? So two things you have to do. You have to come up with the regularizer, you have to come up with the loss function, and you have to come up with an algorithm for computing gradients for all of them. Okay? And then you're going to be updating your parameters. Alpha is going to be your learning rate. It is not a very important hyperparameter to pick for the update. Training epoch equals iteration of all examples. So sometimes people say, you know, I've trained my model for 10 epochs. It basically means one epoch means a single pass through the data, right? If you're at a big tech company, typically the number of training epochs is 1. You just can do just one pass through the data. That's about it, if you have a lot of data. So to train this system, to train parameters, or to train this neural net, what do we need? We need loss function. We need procedure for computing gradients. And we need regularizer and its gradients. So those are the things that you need to define when you're designing training algorithms for these models. Okay? Let's look at the loss function. So let's start by considering classification problem with a softmax output layer, right? So we try to build a classifier. What do we need? We need to estimate probability of class C given the data, right? The probability that a particular target takes value C given the input. Remember last class, we've looked at the multinomial distributions, and we've looked at 1-of-k encoding scheme. That's exactly what we're going to be using here, 1-of-k encoding scheme. Now, we can maximize the log probability of the correct class given an input, and that's going to be our target, right? We're going to be maximizing the log of the probability of correct class given the input. And that's going to be our training procedure for classification, right? Which should make sense. Our model is going to be spitting out probabilities. It's going to be spitting out probabilities for class 1, class 2, class 3, class 4, class 5. Our target, the training, is going to be saying, predict probability that the probability of the correct class is 1 and everything else is 0, right? That's going to be the maximum likelihood solution. Alternatively, we can minimize the negative log probability. So if we take the log probability and take the negative of the log probability and look at the sum of all classes, this is nothing more than a cross-entropy error function, right? This is, by definition, is a cross-entropy error function. So here you're basically saying sum of all classes, this will only be 1 for the correct class and 0 for all incorrect classes. And so you try to maximize the probability of the correct class. This is known as the cross-entropy error function for multi-way classification problem. And that's what you will implement in your homework. Okay? And again, look at the deep learning book, look at the Bishop's book, it kind of goes through this cross-entropy error function pretty in detail. You know, if I think about neural nets, particularly, they're heavily used for classification problems. And for classification problems, cross-entropy is your friend, is your best friend. So you should have, you should kind of softmax, cross-entropy, those things you should be very familiar with. Okay, procedure for computing the gradients. So let's remind ourselves what the neural network is. You have pre-activation, right? So for example, pre-activation here is take the weighted average over here, and then there's a pre-activation for this node. And then there is hidden layer activation, where you take pre-activation, you pass it through nonlinearity, and you get activation, and so forth, and you repeat it however many layers. And then you have softmax activation function. So now, what do we need to compute? we need to compute the gradients of our cross-entropy error of the output with respect to the parameters and of this entire network. So let's look at some of the settings. Let's take the gradient with respect to f of negative log of f, right? Remember what the definition here is just the probability of predicting correct class. So you take the gradient, log 1 over f, you have 1 over f, minus remains, you have this. This is partial derivative with respect to each particular output out of the neural net, right? Remember, we're going to have 10 of them if we have 10 classes. If I look at the actual gradient, I'm going to have this representation, right? Which is, again, think of this as an indicator function. It's telling you which class it is, 1 minus f of y. So this is just taking gradients of your loss with respect to these guys, okay? Now, if I take the gradients with respect to pre-activation, right, of this term here, I can use chain rule. And on the next slide, I'll show you the chain rule. But you can basically take the chain rule. So you can take derivative with respect to f, and then you take derivative of f with respect to a. Now you're going to have this expression here. And if you look at the overall gradient, you're going to have this expression. What is this expression telling us, just at the intuitive level? Any guesses? Yes?
What direction you need to go, that particular neuron needs to go in?
Sure. But remember, this is an indicator function. So let's say I have 3 classes, right? And for this particular input, class 1 is the correct, class 2, class 3 is incorrect, right? That's my data. My input belongs to class 1. This is going to be a vector 1, 0, 0, right? What is this going to be? Output of the neural net as a softmax. It might be 0.7, 0.2, 0.1, right? What is this objective doing? It's almost like it's the same gradient as sum of squared errors. It's essentially telling you, change the parameters of this function f in such a way that the output here would be 1, 0, 0, right? Because here you have its correct class is 1. The second class and third class are not correct. And so what I'd like for my f to be, I'd like for my f to be 1, 0, 0, in which case the gradient is going to be 0, right? So that's what the gradient with respect to the pre-activations is doing at the top level. It's basically saying, make sure that my output predicts correct class with 100%, with probability 1, and predicts incorrect classes, with probability 0s. That's the maximum likelihood learning rule. Of course, it's not perfect. And that's why we will need regularizers, because to get, for your model to really predict 1 using softmax, remember, these are functions. You have to have very, very large weights, right? So the regularizers will come into place. But that's roughly what this objective is trying to do. This is the derivation. Okay? So this is actual derivation. You take the derivative with respect to f. You take derivative of f with respect to pre-activation. This is softmax function. You unroll the softmax function. You take the gradients. You take the gradients from the softmax function. You get to this solution. Okay? And that's what you're going to do on your midterm. No, I'm joking. This will not be on the midterm. So, but for those of you, again, just for your own exercise, just go through it. It's like, I don't know, like a 3rd grade algebra that you just tediously have to go through and derive and exponentiate and take the derivatives of x and do a little bit of bookkeeping. Okay? But do go through this slide. And that's your kind of like your first year calculus rule of differentiating by parts, or like taking derivatives properly. So make sure you know that. I'm not going to be testing you on that, but you should know that. Maybe once you start looking for a job, somebody will ask you that question. I've seen that on the interviews. Is the softmax function, derive me the gradients of that, right? So you should be able to do that. Okay, now, how do we get gradients with respect to the hidden layers, right? Now, this is where it's getting a little bit more complicated. Now you have to backpropagate gradients all the way down through the network. By the way, you're going to have to implement this anyways in your homework, your first assignment. So you'll get to do a little bit of math. So now this is getting complicated. But here's the trick. The whole backpropagation algorithm at the high level is nothing more than a chain rule, right? Think of the neural network as you have the input, take the linear combination, you pass it through nonlinearity, take the linear combination, pass it through nonlinearity. So if you write down the whole function, it's kind of a function that has a bunch of compositionality to it, right? Take a linear combination, nonlinearity, linear combination, nonlinearity. So if you write down mathematically, this is just a function, it's just a continuous function with a whole bunch of nonlinearities. Everything is differentiable, right? And so when you compute the gradients of your loss with respect to all the layers, all the parameters, it's nothing more than just bookkeeping and using chain rule, okay? And the idea is the following. If you have some function that can be written as a function of intermediate results, then you can say, if I take the derivative of this function with respect to A, I can take the derivative of function with respect to QIs and take derivatives of QIs with respect to A and sum over QIs, right? This is the chain rule, right? So if you want to compute the derivative of something with respect to A, you can compute the respect to intermediate terms and so forth. So that's exactly what we're going to be doing. We're going to take derivative with respect to this, and then summing that up and taking derivative with respect to pre-activations and so forth, okay? So in this case, A can be a hidden unit, QIs can be pre-activations in the layer above, and PA can be the loss function. Okay, so let's see how it works. Let's take the gradients with respect to the hidden layers, with respect to these hidden units. So partial derivative with respect to a particular hidden unit at layer K, a unit J. So let's say this is level K, unit J, right? And we take the derivative of the loss function, which is the cross entropy. Well, by the chain rule, we can take the derivative of the loss with respect to the activations at the layer above, and then take derivative of these activations with respect to the hidden units. And remember, what's A sub K? That's what it is, right? It's just a linear combination plus the bias. So now if I look at this derivative, what is this derivative? This derivative is just Wij, right? So that's the derivative. So now we have this expression. But now before, in previous slide, we've actually seen what this thing is, taking the gradients with respect to the pre-activations for the softmax function, right? And that's exactly what we're going to get here. If we take derivative with respect to the hidden units, we're going to have Wk plus 1. And this is exactly the gradients with respect to A, which is going to be the delta function, right? And we already know how to compute this. This is just going to be the difference between the indicator and your predictions. All right, so we already computed this, and we've just computed that. So now it gives us gradient with respect to these guys. Okay, so we're backpropagating gradually through the layers of the network. Loss gradient with respect to pre-activation. So now let's compute the gradients with respect to these pre-activations. It's the same thing. We can take the gradients with respect to H case, and then we can take the gradients with respect to A case. Okay? And now this is the definition. We take the pre-activations, we pass it through nonlinearity. We've already computed this point, right, at the previous slide. And now we're just computing this gradient. What is this gradient? Well, it's the gradient of the nonlinearity, right? If you look at this expression and say, what's the gradient with respect to A case? Well, it's just the gradient of this nonlinearity, right? And we already know what that is from the previous slides, right? So this is, again, nothing more than just a backpropagation rule, just a chain rule by gradually backpropagating through the whole network. Yes?
So that the derivative would be of a nonlinearity, but what if we're using value, which is step, or has an elbow?
Yeah, we'll come to that. So let's actually, so if I actually look at the whole gradient, right? The whole gradient is going to take this form, which is the gradient with respect to the hiddens, right, of your loss function. And this is element product of all of these nonlinearities. however many hidden units you have. Okay? Because you can just stitch them together. And this is just done for efficient, when you're coding this up, you don't want to have a bunch of for loops. Take the gradient perspective, unit number 1, unit number 2, unit number 3, so you can vectorize it. And that's something that you'll have to do for your homework as well, try to vectorize the whole thing. Yes?
So the stochastic part of this, is this just we define a loss function that, so something like softmax that takes account of probability?
So the stochastic gradient descent part of it is different, because the stochastic gradient descent is basically saying, I'm just going to take one example, or maybe 10 examples, right? And just compute gradients for those 10 examples. What we're doing right now is we're computing gradient for a single example, right? Once we compute the gradient for a single example, we can average these gradients over 10 examples and then do the update. Or we can average over the entire training set if you don't have enough, if you have smaller data sets. That's going to be batch training. Right now, we're just computing the gradient of a single example. And then we can average over all the training examples. Okay? Okay, so this is the gradient of the activation function. So how do we compute the gradients of the activation functions? So let's look at this. If you have a linear activation function, then it's just 1. Easy. If you have sigmoid activation function, the gradient is just sigmoid 1 minus sigmoid. Okay? So sometimes when people use these nonlinearities, notice what happens. G of A is a number always below 1, right? It's always less than 1. So if you think about gradients, if you have a number that's less than 1, and this is another number that's less than 1, when you multiply them together, you'll have a number that's even smaller than 1, right? And sometimes this is known as a gradient vanishing problem. Because if you have 50 layers, by the time you get to layer 25, this effect accumulates. It will also be the problem for recurrent networks. When we repeat the same procedure many, many times, when you backpropagate, this messes you up, right? So you're always going to be scaling the gradients down. So what's happening with these neural networks, you're going to have a strong signal from the buff saying, change these parameters of this layer. By the time you get down to the last layer, your gradients are going to be pretty weak or fairly small because of this property. If you're using 10H function, the gradient of the 10H function has this form, which is, again, a number sort of smaller than 1. So you have the same problem. If you have rectified linear units, it's actually not that bad, but it causes some other problems, like stability problems, because it's unbounded. So if you take the partial derivative, you just basically have this property. It's 1 if it's positive, otherwise it's 0. Okay? A lot of people who kind of like work on optimization basically say, well, what happens here? What happens at 0? What would you do? Yeah?
We are getting a small adjust as our record.
Okay. No? No guesses?
0.5.
The what? 0.5. 0.5, okay. Any other guesses? Coin flip, okay. So let me ask you a different question. What's the probability that in your gradients you will see exactly 0? So does it matter? In practice, it doesn't matter. If you kind of like try to prove something about it, then it matters. But in practice, the chances you're going to hit exactly 0 is basically 0. You'll never hit like, take some linear combination, it's exactly 0, right? So, it basically, it's not a problem. And now, again, it might be some instability around here, but at the same time, it's okay. There are ways of dealing with that problem. Yes?
Is this value activation function the only solution for the gradient vanishing problem among these 3 activation functions?
Not really. I mean, it also has its own problems. We'll later on in the course, we'll come look at different architectures. like having skip connections and such, so you can reinforce the gradient when you're backpropagating it. But it's not really the solution. Okay. Now, let's come back to computing the gradients. Let's just remind ourselves. Now, let's compute the gradients of the parameters. That's what you will actually need to train these models. So let's look at the partial derivatives with respect to these parameters, right, of the loss function. Well, remember, we have this property here, right? That's a pre-activation. So now if I take the derivative with respect to A, pre-activation, I take the derivative with respect to W. If I take the derivative with respect to W, what do I get? I get H's, right? So now that's going to be my gradient with respect to these parameters. And again, this is nothing more than bookkeeping. I know, and if I look at the gradient itself, it has this property, right? It's the gradient of the cross entropy, which is again going to be the difference between the indicative function and your prediction, times the H, right? And that's going to be the gradient with respect to these parameters. And that's going to be gradient with respect to these parameters. Now, you have to be careful to figure out where to put transposes and stuff. So when you are debugging your code for these things, try, having different number of hidden units in each layer. Because if you have 100 units here, 100 units here, and you're trying to debug the code, you have 100 by 100 matrix, and it's like, transpose this way, it will work, transpose this way, it will work, right? It's a very good debugging tool, just to make sure that these things match up. Of course, if you're good in math, you will know exactly where the transposes are. If you're not, try using the tricks to figure out that this is correct. Now, gradients with respect to the biases, it's exactly the same thing. You take the gradients of the cross entropy with respect to pre-activations, and then with respect to the biases. And when you take the gradients with respect to biases, it's just one. Okay? Sometimes it's more convenient to code the system up where you don't have separate gradients for the biases, but you actually add an additional hidden unit that's always one. And it doesn't change, right? And so then you can just say, here's my H, where one of them is always one all the time. It saves you on coding. And this is the gradient with respect to the biases, exact same way as you do the gradients with respect to the parameters. Okay? So now, how do we do backpropagation? You perform forward pass, right? Take the linear combination nonlinearities. You have your predictions. You compute the gradients of the cross entropy before the activation, which is this quantity, right? How good your fit is. This is your prediction. This is just the indicative function. 0, 1, 1 for correct class, 0 for incorrect class. For multiple layers, you compute the gradients with respect to the parameters, right? We know what this is, times HK, and the biases. And then we compute the gradients with respect to the hidden layer below. So we compute the gradients with respect to H's. And then we compute the gradients with the hidden layer before the activation, right? Because notice that we need this to compute this. Right? So here, the gradients of the hidden units before the activation, and then we multiply it by, you compute this, and you scale it by nonlinearity. Okay? Now, a point for your homework, these equations in Python or MATLAB, you'd be on the order of maybe, if you vectorize it properly, if you have a network with 3 layers, could be about 8 lines of MATLAB code. 8 to 10 lines of MATLAB code, right?
But it was not recommended, right?
The what?
It was not mandatory.
No, it's not mandatory. I'm just saying, like if you think that there's like a big software engineering project where you have to compute the gradients with respect to, each node and, you have thousands of nodes and so forth, no. Everything is standardized. Everything can be vectorized, right? It really is, like if you look at these equations, it really is vector, vector. This is another vector matrix. This is a vector times matrix. It's another vector. Scaling up, it's another vector. That's it. right? So that's how, like if you look at software implementation of backpropagation algorithm, that's basically what it is, okay? But for your homework, you will play with it. I mean, you can, if you haven't vectorized things before, like in Python or MATLAB, you're more than welcome to run for loops and take the derivative with respect to each one of the neurons. If you do it in C, you can compile it. Maybe it will run fast. But if you do it in Python or one of the scripting languages like MATLAB, Python, you can actually make it very efficient. Okay? Like most of the systems, if you have a big image and you build 100 layers, typically it takes about a second to do backpropagation pass, right? So for your homework, it should be on the order of like milliseconds to do the backpropagation pass. Okay, so the computational flow graph, just the way people view these systems is that you have a forward propagation, can be interpreted as an acyclic flow graph, right? Given the data, you compute the pre-activation, you compute the hidden unit activation, pass it through nonlinearity, pre-activation, and so forth, right? So it really sometimes is called fprop method. For each box in the right order yields for the propagation. That's how people structure the code. There's a block, there's another block, it's another block, and it's the same operation for every single block. And the backpropagation, you basically compute the gradients of the loss function with respect to all of the parameters here. And you essentially, the way to think about this, you're computing fprop almost like in reverse order, right? So while forward propagation output depends on the children nodes, backpropagation depends on the parents' nodes, right? So that's why the forward propagation starts with the data, makes a prediction. The backpropagation computes the gradient and does it in a backward pass, just by using chain rule, right? Okay, so this is the algorithm. We know what the loss function, cross entropy. We know how to compute the gradients. Let's look at the regularizer. Yes?
What is T?
T is the number of training examples. Oh, sorry, T is the number of epochs or the number of updates. If you're using stochastic gradient descents, you're going to be updating after every single example or after seeing 10 examples or 100 examples. Most commonly used cases is that you batch it up, you take 100 examples at random and you compute the gradient averaged over 100 examples. And then you take the next 100 examples, compute the gradients and so forth. Yes?
So in that equation right there, are you computing all of the training examples together as just basically a matrix?
Yeah, that's right. So here it depends what your choice is. On your homework, you can either do a batch, which is computing the gradients for all examples and then averaging the gradients, or you can use stochastic gradient descent. You can do mini batches. You can stitch together into mini batches of 100 and update after seeing 100 examples. It's up to you. For the homework, you can just do batch training. You don't have to do stochastic gradient descent because the data sets are small enough that you can just compute the gradients for the whole training set, take a step, and then compute for the whole training set and take a step. Okay? So it's designed not to be a large-scale experiment so that you can actually do debugging for your first homework. Okay, let's quickly look at regularization, and we'll come back to this next class. L2 regularization, something that you will be implementing for your homework, which is nothing more than just a Frobenius norm of your weights, just sum of the squares. Okay? The gradients, very simple, right? Only applies to weights, not biases, and this is called weight decay. It's also sometimes can be interpreted as having a Gaussian prie over the weights while doing map estimation. We'll later look at the Bayesian methods for deep networks, Bayesian neural networks. But again, weight decay can be loosely interpreted as kind of very poor Bayesian approximation to the posterior. Okay? But nonetheless, what is this doing? This basically regularizes is saying that you want to keep your weights to be small. You don't want your weights to be large, right? You want them to be close to zero. And on your homework, you will see that regularizer actually can help. It can help, substantially. Other regularizers, remember we've looked at this in our first class, right? Other forms of the regularizers could be lasso, it could be quadratic, it could be other forms. Okay? So for the L1, we can just take the absolute value of the weights, and the gradient is just a sine of W. Right? So it's 1 if it's positive, it's negative 1 if it's negative. If your weight is positive, it's +1. If your weight is negative, it's -1. Yes? So we haven't really looked at it. Maybe we can come back to this later because we need the notion of the prior and the likelihood and such. This is more for people who've worked with the Bayesian methods. There is a connection between map estimation, maximum a posteriori, and the weight decay. We'll come back to this later in the class. So, and again, this can be interpreted as Laplace prior over the weights. So L1, L2 is a corresponding sort of Bayesian connection to doing linking the two. I don't have time to go through these Bayesian connections. We'll look at that later in the class. But nonetheless, for you to think about this is something that people have used before as well. Because what this gives you is actually, if you're done properly, it kind of sparsifies a lot of the weights. So you end up with a network that's fairly sparse. Because most of the weights are going to be 0. Exactly 0. So L1 will push some of the weights to be exactly 0. And there are a few papers trying to do that, particularly for people who want to deploy these models on mobile devices and don't have enough memory. So you can, prune down a lot of weights. Let me just remind you on the bias variance decomposition. Remember in one of our classes, I think a couple of classes before, we've looked at the expected loss. And remember, we decoupled expected loss as bias squared, variance, and noise. Right? And what's the bias? The bias is the average predictions over all data sets, how they differ from the optimal function. Variance is solution to individual data sets vary around their averages. Right? And then there's some intrinsic noise. Right? So bias essentially is telling you, if I have a complicated function, my bias will be fairly small because I can fit anything. But my variance will be large because I only get to see one data set. So if I fit that complicated function, it might exhibit some oscillations, right? And the other way around. So you always try to, trade off one versus the other. And remember, in last class or a couple of classes before, we've looked at the notion of regularizer. And that's exactly what's happening here. Because your regularizer, if you set it to be too high, your bias will be high because you're going to be training a fairly simple network. Because you're going to be forcing all your weights to be 0 or close to 0. So you're going to be in this regime, right? Variance is going to be small, but bias is going to be high. If you don't regularize and you fit these complicated big neural nets, then you're going to have small bias, but you're going to have high variance, right? So that's not optimal. And then you basically always try to find some hyperparameter choices that are optimal in your case for your data set. So you can generalize as well as you can. Maybe you introduce some bias, but you're reducing variance. Okay? And so this is also in the context of neural networks. So generalization error, when we try to build models that can generalize, can be seen as a sum of the squared bias and the variance, right? And this is, a setting where here's my optimal function. If I build a very simple neural net, then I'm going to have low variance but high bias because this is a space of all possible functions. And whatever I fit here is going to be far from the truth. But because it's so small, no matter what data set I see, my functions will not differ that much. So I'm going to have small variance. Here's you have high variance, low bias. Here's a space of all possible functions I can fit. I can build you big, gigantic neural net. I can fit anything. In fact, there were papers that show you can fit random noise almost perfectly, right? This is an example of that setting, right? Obviously, the truth is out there. And maybe if I give you enough examples, I can get there. So I'm going to have low bias because it's there, but it's going to have high variance. And you're sort of always trying to come up with a good trade-off between the two, right? And how do we do this? Well, regularization is one way of controlling capacity of the neural network, right? And then your homework, you'll play around with the regularizers, you'll play around with the size of the network. It's another controller, how big your network is, how many parameters you have, and so forth. Initialization, and just a couple of slides that I need to get through so that you can start working on it. You can initialize biases to 0. For weights, you cannot initialize weights to 0, particularly with 10H activation functions, even with sigmoids. Because for 10H functions, all gradients would be 0, have a saddle point. All weights are doing exact same thing. So if you backprop through the whole thing, you'll see that for 10H, you'll hit 0. For sigmoids, for ReLUs, these are not going to be zeros, but you always want to do symmetry breaking. So you also can't initialize all weights to be the same value, right? Because all hidden units in LA will always behave the same. So you need to break the symmetry. And so a good strategy is to sample weights from uniform minus BB, where B is square root of 6 divided by HK minus 1, where this is the size of the kth layer, and this is the size of the kth minus 1 layer. Okay? So if you're building a model where HK has 100 units and this has 200 units, you basically say square root of 6 divided by square root of sum of the two.
Where does the square root of 6 come from?
Square root of 6 comes from whenever you're working with sigmoids. They're saturating at 3 and 3. So you basically, if you're initializing it with sigmoids, you kind of want your total average, the weighted average, to be close to 0, but with some variance around 0. And that basically ensures that you're not initializing the ways that for some hidden unit, you take the weighted average, and the weighted average is 10, right? Sigmoid of the 10 is going to be 0.99999. You compute the gradients. The gradients is going to be 0.99 times 0.001. Remember, the gradient sigmoid is 1 minus sigmoid. You have this basically mess when it comes down to computing the gradients. So this just ensures that whenever you're using, and it also works fairly well for ReLUs as well, that every single, when you take the weighted average coming to a particular neuron is always, centered around 0 if you're using 10H, or centered around 0.5 if you're using sigmoids.
So this is uniform, right?
Yeah.
What if you be creative and then Gaussian?
Yeah, you can use Gaussians, you can use uniforms. There are like 10 papers written on how to initialize these models. So people doing all kinds of stuff. You can also sample from a Gaussian with some small variance. That will ensure that the weights are not crazy and that they are different. That's something that you can try in your homework. You don't have to use this initialization scheme. You can just sample from a Gaussian. But just make sure that when you diagnose your system, it's not like some units saturate and you can't really compute the gradients. Model selection, remember we've done this for your homework. You're going to be training on the training set. You're going to be using validation set to choose hyperparameters. Layer size, learning rates, all the good stuff, number of iterations. And then you're going to be estimating your generalization on the test set. Right? And that's the goal. How well can you do on a test set? Right? So for your homework, you're going to have 3 sets. You're going to have training, you're going to have validation, you're going to have test. The hope is that you're not going to be picking up on the test examples as much. So use validation for your validation. And that's kind of the behavior you should be seeing, right? As you keep training or you don't regularize your model, your number of, your training area will go down, eventually your validation area will come up, and you basically pick these parameters. Or you can do early stopping. Early stopping works very well in many of these models. So you kind of figure out when is it that you need to stop. I think computer scientists invented it, when machines were slow. So you're training your model, and it's like, oh, well, you don't have to train it for a long time. You can just stop. And we're going to call it the regularizer. It's actually pretty good. It works pretty well. Sometimes it's very hard to beat this. Right? Tricks of the trade. Maybe I'll just go through this, and we'll stop because we're running out of time. And I'll stop here. Whenever you're working with the data, not for your homework, but in general, it's a pretty good idea to normalize your data. So for each dimension, you subtract the mean, and you divide by standard deviation. So basically, all the inputs are normalized. All the inputs are 0, mean variance 1. So it's not like you have an input here, it takes value 10, this input takes value minus 100, and it's just the network has a hard time figuring out what's the scale. Learning rates. Start with a large learning rate. Start with 0.1. In fact, for your homework, start with a learning rate of 0.1. Works pretty well. It's going to be hard to beat. 0.1, 0.01, and then you're going to be, trying to scale it up and such. Okay, next class we're going to continue on the second part of neural nets.